Welcome to session 17 of the Competent America video series. This session addresses fossil fuels and climate change. It's a difficult and in some ways a tragic issue. We have this massive fossil fuel industry, coal, oil, and natural gas, that has served the nation very aggressively for a very long time. And if there were no other issues around, we would probably hang on to it for quite a long time to come. Here's what I hope you will remember. Carbon dioxide is up 41%, rising rapidly. Carbon dioxide weakens the Earth's ability to cool itself. Emission reduction is not enough. The real solution is to adopt a clean energy portfolio. There are four major topics. I will start with the size of the problem. Fossil fuels are very popular. Buildings use natural gas, vehicles use petroleum, industry uses all three fossil fuels, electric utilities use coal and natural gas. This produces an extraordinary amount of consumption. Coal. We have been running about 1 billion tons a year of coal. Petroleum, 7.5 billion barrels a year. Natural gas, 22 trillion cubic feet per year. The natural gas numbers are rising, coal numbers are shrinking. We don't know yet whether the natural gas rise is permanent or simply seasonal. Collectively, all of this consumption produces almost 6 billion tons of carbon dioxide a year from the citizens of the United States of America. Now, measurement question. Are we talking tons, metric tons? Are we talking parts per million? On the ground, governments measure carbon dioxide emission in billions of tons. In the atmosphere, however, scientists measure stocks of carbon dioxide in parts per million, or ppm. Tons, parts per million, how are we to keep that straight? I will use tons rather than parts per million at every chance I get. 1 millionth part CO2 in the atmosphere weighs 7.77 billion tons. So the pre-industrial norm for carbon dioxide in the atmosphere, 280 parts per million, weighs about 2,175 billion tons. Now for some CO2 rough rules of thumb. If global emissions equal 30 billion tons a year, of which the United States has roughly a fifth, then about 8 billion tons get taken up by forests. That is a fluctuating number. Sometimes forests take more, sometimes they take less. Of the remainder, about a third, or 7 billion tons, let's say, will be absorbed by the ocean, and about 2/3 will remain in the atmosphere. If it were 3 billion tons, the ocean would take 1 billion tons, and the atmosphere would get 2 billion tons. There was a constant and steady proportion maintained between ocean and atmosphere. 15 billion tons added to the atmosphere represents about 2 parts per million. Let's look at where we are. On the left axis, in billions of tons, 2,000 billions of tons up to 3,200, you will see a dark line just a shade below 2,200 billion tons that represents the pre-industrial norm. Look at the jagged red line that's rising across this. The line sinks when the northern hemisphere is in summer and northern hemisphere plants are taking up carbon dioxide. It rises again in the winter when northern hemisphere plants are giving off carbon dioxide. In 1958, it was about 12 or 13% higher than the pre-industrial norm. Now, in 2012, it is 41% higher than the pre-industrial norm. In 2011, there was a 16.5 billion ton rise in the total atmospheric overload of CO2. You can't see it easily on that previous chart, but the rate of increase is actually accelerating. In the early 60s, we added 5.8 billion tons a year, on average. In the later 60s, 7.7 billion tons, and so on. We're now in the 13, 16.7, 15 billion tons a year range. Here's the fossil fuel takeaway. The atmospheric stock of carbon dioxide up 41% from its pre-industrial norm. This overload is growing at 7% a decade, and there is a ratchet effect. Once the forests and the ocean have taken their part and the rest of the carbon dioxide gets in the atmosphere, that portion of our emissions stays for a very long time. We cannot really go back. Next, to the Earth's natural cooling system. I have just said emissions are accelerating globally. The stock of CO2 is growing. Why do we care? Well, we care because the Earth takes in loads of energy from the Sun, roughly 2.9 million terawatt hours a day worth of solar energy, which I show here as being visible light, although there is a little ultraviolet and some infrared included. That's a lot of energy over a 24-hour period over the entire surface of the Earth. Why doesn't the Earth just get hotter and hotter and hotter? Maybe the Earth has its own cooling system. Cars cool themselves using radiators and water. People cool themselves by sweating. Dogs cool themselves by panting. How does the Earth cool itself? The Earth cools itself by radiating infrared energy back into space. Some from the top of the atmosphere, some from the middle of the atmosphere, and a bit directly from the surface of the Earth. This is the Earth's natural cooling system. And I show it here. Under equilibrium conditions, energy out equals energy in. If we get energy in at 2.9 billion terawatt hours a day, we will put energy out in the infrared spectrum at 2.9 million terawatt hours a day worth of infrared. I show the infrared spectrum. If we look here, we see the spectrum from, let's say, 3 microns to 50 microns, and this arrow represents the 15 micron wavelength of the infrared spectrum. This is the wavelength that has always been suppressed by carbon dioxide. But under steady state conditions, the entire infrared spectrum radiates just as much energy back into space as the Earth receives in the visible light spectrum from the Sun. In other words, infrared cooling allows the Earth to maintain a stable average temperature unless new CO2 reduces energy out, less energy out in the 15 micron portion of the infrared spectrum. We shrink that by a few thousand terawatt hours a day because we're not punching quite as much energy into space in the 15 micron portion of the infrared spectrum as we were. With energy out shrinking, the Earth gets warmer. Now, it doesn't warm rapidly. The oceans of the world soak up most of this new energy, and they do it to a depth of a few hundred feet at least. We won't really see the climate impact of the carbon dioxide we have added today for some years yet, because it will take the oceans that amount of time to warm up enough to really affect the temperature of the planet and affect the climate. But once the oceans have warmed, they're going to hang on to that warmth for a very long time. How much warmer is the Earth getting by this process? Scientists tell us that we are warming the planet at a rate of 2 degrees Celsius per century. When I was a kid, they called that centigrade. Or 0.2 of a degree Celsius per decade. Or if we break it down on a daily basis, that works out to about 1/18,000th of a degree per day. Now, who among us can notice that amount of warming on a daily basis? Not a single person can physically detect that increase in daily warmth. And yet, added up, day by day, year by year, decade by decade, we begin to notice a real difference. So here's the takeaway. By boosting atmospheric CO2, we interfere with the Earth's natural cooling system and we stimulate global warming. Interesting. So what kind of problem is this? Is it an emissions reduction problem, as the environmentalists have been claiming it is for quite some time? Let's think this through. Here again, I look at cumulative carbon dioxide in the atmosphere, the total stock, starting at 0 and going all the way up to 5,000 billion tons. And over to the left, I show historic carbon dioxide from 1960 to 2010, rising to just a bit above 3,000 billion tons today. Let's imagine, for the sake of argument, that extreme danger begins once carbon dioxide reaches 4,000 billion tons, almost double its pre-industrial norm. And let us further imagine that with a faster emissions scenario, an extrapolation of what we're already doing, that we hit that danger zone in about 2070. Now let us imagine that we go to a slower emissions scenario. In the slower scenario, the total stock of carbon dioxide rises more slowly, and we don't reach the danger zone until, say, 2090. Well, does that really matter? 2070, 2090? In a slower emissions scenario, we burn the same amount of fossil fuel. Either way, it just takes a little longer in the slower scenario to reach the danger zone. But no matter when we reach the red zone, the same amount of damage is in store for us. The only safe solution is to cap the stock of CO2 below the red zone. Here I show it at 4,000 billion tons. There are those who argue it should be 3,500 billion tons, and that we will really be in trouble if we don't cap it at 3,500 billion tons. So here's your takeaway. Emission reduction is not a solution. It delays the disaster by a relatively trivial amount. It is not the path to take if we want to prevent the ultimate disasters of climate change from occurring. So if emission reduction isn't the answer, what is? Well, let's look at the problem logic and the solution logic. First, the problem logic. The energy technology we have leads us to consume fossil fuels. The fossil fuels we consume lead us to produce carbon dioxide emissions. Those emissions add to the total stock of atmospheric CO2. And the greater the stock of atmospheric CO2, the greater the warming. The greater the warming, the more climate change we have, and the more climate change we have, the more humanitarian catastrophe we generate, the more economic catastrophe we generate. Now, think about this. Let me go back. The first 4 steps are governed by rules of proportionality. Fossil fuel consumption is proportional to the amount of energy technology. Carbon dioxide emissions are proportional to consumption. The total stock of atmospheric CO2 is proportional to cumulative emissions. And the total warming we get is proportional to the total stock of atmospheric CO2. But the next step is not a step of proportionality. We don't know how much climate change we will produce for 1/10 of a degree of global warming. Climate change is a threshold question. A tiny change in temperature can lead to a significant change in climate behavior. Climate change is the unknown unknown. We should, at least in broad terms, recognize the dangers. Major damage to agriculture, big threat. There is also a danger, an inevitability, I think, of sea level rise and of coastal cities being swamped. The ice sheets on Greenland and on West Antarctica will be gone within 1.5 centuries, 2 centuries at most, if we continue using fossil fuels as though there were no tomorrow. Third major danger. The more carbon dioxide we put in the atmosphere, the more the ocean takes up. Carbon dioxide in the ocean turns into carbonic acid. The acidification of the ocean threatens species extinction in about 7 or 8 decades. Time to face the music. The CO2 consequences are irreversible. The probable and even the semi-probable damages are beyond measure. And none of the people who have caused those damage will pay a nickel to any of the victims. We have to do something, and to know what it is that we have to do, we have to look clearly at the solution logic. If we are to limit humanitarian and economic tragedies, climate change must be halted. For climate change to halt, global warming must be halted. For global warming to halt, the stock of CO2 must be capped. And if CO2 is to be capped, CO2 emissions from fossil fuels must be halted. To halt CO2 emissions, fossil fuel consumption must be halted. And to halt fossil fuel consumption, a new energy portfolio is required. Tough message, but a competent nation faces that message, thinks about it carefully, and resolves to do everything it can. CO2 is up 41% and rising rapidly. It weakens the Earth's ability to cool itself. Emission reduction is not enough. The real solution is a clean energy portfolio. So there you have it, a very tough issue, a very urgent challenge. Thank you for joining me. Hope to see you next time.